Our last topic area in this course for graphs is the topic related to max flow. And you'll sometimes see this referred to as network flow. And I'm going to, first of all, go over the algorithms for how you solve this in general graph terms, and then we'll look a little bit more at applications later. But just to get the basic idea of what's going on, we will have a source, which I'll usually write over here on the left, and a sink, which I'll usually write over on the right. And there will be some set of nodes in the graph in between, and there will be edges between the various nodes in various directions. And each of these edges might have a capacity associated with it. So for instance, 3, 4, 2, 1, 1, 2, 3, 4, 1. Okay. And the question is, how much of whatever is being produced at the source can get to the sink? Okay, so the source you can think of as an infinite source of stuff, and the sink is an infinite receiver of stuff. It'll take as much as you can give it. And the question is, how much can you push through this? How much stuff can flow through this entire network from the source to the sink? And so you can imagine, and kind of the approach we're going to take is we're going to follow paths along here. And for instance, that path that you see right there, I could put 2 units of flow through that path because the minimum edge along there is 2. So you can imagine, okay, there, 2 units flowed that way. And I might be able to get another unit to flow like that. And so between those 2 routes, I was able to get 3 units total. And then I might be able to get 1 more unit there through the bottom. And so I can actually get 4 units through this graph. Well, the network flow problem, that's its general term. You're going to have a graph with a source and a sink, and you're trying to figure out how much can flow through there. Max flow has lots of applications. There's a lot of problems that can be stated as a max flow problem and solved that way. So it's a useful approach to be able to solve. So the algorithm that we're going to start out by introducing is one called Floyd Fulkerson. And this is a general algorithm. There's actually some improvements on it, and I'll talk about some of those later. It's not the only kind of family of approaches for solving max flow, but it kind of makes the most sense to me, and so it's the one I'm going to introduce. So the basic idea of Floyd Fulkerson is a little bit like I just outlined, which is we will repeatedly do the following. We'll find a path from the source to the sink. So in the graph, we'll find some path. We will find minimum edge weight. On that path, and that's going to be the amount of flow we can push through on that path, the amount we can push through on that path. And then we will reduce the edges of the path by that amount. Now, there is one more key part to this. So this approach so far is sort of the greedy approach that we would take, which is you try to push some flow through, and then you reduce the edges, and you push as much through as you can there, and you reduce the edges, and so on. But there's one key change that we have to make in order for this to actually work to help us find the optimum answer. And that is, we have to actually, we have to actually introduce residual flow back in the, I'll say backward. So the idea of residual flow, and I'm going to do an example that I hope will illustrate this well, but the idea of this residual flow is that this is a way of sort of undoing a greedy choice we made that was not ideal. So you make a greedy choice, you say, I'm going to try to push flow through this path. And it might turn out that, well, I really shouldn't have. I shouldn't have put that much flow through that path. So I need to undo that a little bit. And residual flow is the way that you can do this. So we will add residual capacity. So let me start out. I will show you a graph. I'm going to give you a very simple graph. If you look at the PowerPoints that accompany this, you can see a different graph there that illustrates the same idea. So if you want two examples, look there. But I'll give you a general graph so that we can see how this process works. And I'll start out by showing you the greedy approach and why that does not work. There is one more thing I wanted to mention, which is in the graph that we have, I'm going to assume that we have directed edges from one node to another. If you have a graph that has undirected edges, then you just transform that into one that has two directed edges that can go in either direction. And so if there's some capacity like 3 on this, you would put 3 in each direction. In other words, you can have a flow from A to B of 3 or from B to A of 3. And in any case, the net, the maximum flow in either direction is no greater than 3. And so notice if you somehow had flow of 3 in one direction and then flow 3 back in the other, it's a net flow of 0. And that idea is actually kind of important. So just keep that in mind. That's the way we can model our graphs. But I'm going to just show things with a directed graph because I think that's a little bit easier to see. Okay, so first of all, let me show you the graph that I'll start out with for illustration purposes. So we will keep this fairly simple. So over on the left is going to be my source. Over on the right is going to be my sink. I'm going to have paths like that, so you can see the direction that you can possibly have flow go through. I will put weights on these edges of 5. Remember, that's how much flow is allowed to go along them. I'll do something here, 3, 8, and 3, and I'll set these at 4. Okay, now if you were to actually look at this, you should be able to look at this and say, oh, I can imagine how much goes through. So notice, on one hand, you're constrained. There's no more than 15 units of flow that can come out of the source. And there's no more than 14 that can go into the sink. And it turns out the max flow here is 14. You can get all 14. And if you want to kind of illustrate how that would be, I'll just sketch this very briefly. I could send 3 units of flow there and 3 units of flow there. I could also send 2 there, and I could send 2 there, and then I could send 4 straight down the middle. Okay, so that would be an example of how I would get to the 14. So if you need to look at the graph for a while and convince yourself that indeed you could get 14 units of stuff flowing through this system where none of the capacities is actually exceeded. Okay, so if that is my graph, I'm going to copy this in just a second, and I'll show you how this would work in the greedy approach where I don't have this important aspect of the residual flow backward along each edge. And again, that's kind of the key part to this algorithm. So I'll reproduce this, and then we'll see what it looks like for the greedy case. Okay, so here's the same graph that we had before. Remember that we have over here, we have a source, and over here we have our sink. And it's the same graph, it's just reproduced a little bit larger so that I can illustrate. And I'm going to use kind of this greedy approach. Now, I will say you can look at this and you can probably say, oh, I see good paths to pick. And I'm going to pick things that are purposefully not as good, because when you write a general algorithm, you can't just tell the computer, hey, I see this and it looks good. You need something that's found automatically. Okay, so I'm going to draw one path at a time, and we'll illustrate the amount of flow that we get through at each stage of this path. So the first one that I will trace is I'll go up to here, down to there, and over. And if I look at that blue path, the most flow that I can have along that blue path right there is 4 units of flow. There's 4 units available there because that's the minimum edge. And then I'm going to subtract off and reduce the weight of each edge by that amount. So this then becomes 1, this becomes 0, and this becomes 4. Okay, in other words, I sort of used up 4 units of flow along this first edge across the top. That I used up 4, I used up 4 coming down there, and I used up 4 of the 8 coming across that way. So after that, I go and I want to pick another route to go. And I might say, well, I'll stick up here at the top, and it looks like I can travel this route to here and over to there. So along the green route, notice the maximum I can get at this point is 1. I can have exactly 1 unit. So there is 1 unit of flow that I get along the green path. And then if I reduce the weight of the edges along there by 1, this will now become 0, and this will become 2. Okay. Then I might pick the next path. So just sort of moving down a little bit. If I look here in this kind of along the middle route, I can go from there to there and there to there. And the most I can get along the yellow route is 4 units of flow because that's the minimum that we see there. So I get 4 units there. That means that I need to reduce the path by 4. So this now becomes 0. Okay, and then finally, I'll follow this kind of bottom path down here. I can go from there to there, and there to there, and the purple one, the most I can get is 3. And again, taking 3 units off of each of those, this now will have weight 2, and this now will have weight 0. Okay, and at this point, there's no more flow that I can get through this graph. There's no way that I can push any more flow from the beginning to the end, and this totals 12 units of flow. Now, you might remember from looking at this before, we should be able to get 14 units through, and this approach just did not work. We could not get all of the flow through the graph that we wanted to. We got stuck along the way. So with Floyd Fulkerson now, we're going to take the same approach, except we're also going to introduce residual edges. So I'm going to go ahead and replicate this graph, or the original version of this graph, and we'll show how it would work with Floyd Fulkerson along the way. Okay, here is the same graph reproduced. Now, this might not look like the same graph that we had up here to begin with, but what I've done is I've taken the original graph that was up here, and I have introduced reverse edges along each of the directed edges that has weight 0. So if there was not an edge already there, I've gone ahead and introduced that. So this is the same graph, the same amounts that we had before, same directions, all of that. But I've got these reverse edges, and this is what's going to let us capture the residual capacity at each step. Okay, so I'm going to proceed the same way that I did before. I'm going to show you the same steps, but I'll show you what gets updated each time. So if you remember previously, our first path was there to there to there. So following the blue path. And again, just like before, we could have 4 units of flow. I'll just show you to remind you that was the same path that we had there. And now, not only are we going to reduce each of those edges by 4, so that this becomes 1, and this becomes 0, and this becomes 4, we're also going to add residual capacity going back in the other direction. So we put 4 units back in this direction, we put 4 units back in this direction, and we put 4 units back in this direction. And the way to think about that is that the residual capacity is a way of undoing flow that we had previously. So if it turns out that we really didn't want to send some of that flow along those edges, I can send some of the flow, I can later have flow that goes backward. In fact, we'll see that. That kind of undoes some of this work. And by undoing it, that's going to let us achieve a better overall result. Okay, but at least the first few stages of this are going to proceed just like before. So we start out with the green path. We've updated it. We've updated our residual flows along the way. Or sorry, that was the blue path. We'll now go to the green path. Again, same green path we had before. Okay, so the green path here, we can only get 1 unit through there. And we will adjust all of the capacities along the way. So this 1 becomes 0, and we add 1 in the reverse. And instead of 3, this one up here will become 2, and we will add 1 in reverse. Now, I will mention, just as a note, anything from the source or the sink, you actually don't need to put the residual edges in. You never end up using them, but it's often easier just to create the graph and put every edge with the residual edge going the other direction, just so that it's there. But it's not technically something that's needed. Okay, so then, kind of like before, we can have 5 units. The middle path, which can have 4 units. So we'll have 4 units of flow there, and we will reduce the flow along there by 4 units. So this 5 becomes a 1. We send 4 back on the residual. This 4 becomes 0. We have 8 back on the residual. And we're done with that. Then the next route that we had was the purple route. It was following this path and this path, and this was a total of 3 units of flow. And just like before, we will reduce the amount of flow available on each one, so that 5 becomes a 2, this 3 becomes a 0, and we have 3 units that go backward on that path. So we increase each of those by 3. Okay, and now, previously we were stuck. This is where we had to stop. But now, with this approach, by introducing the residual capacities, we are not actually stuck at this point. In fact, we can continue to put flow through this graph. And so I'll trace through in red the path that we can follow that lets us get an additional 2 units of flow through the path. So we will go from there to there, and notice we can go from here up to here. And now this is the key part. This is the part we weren't able to do before. We can go up to there and then follow that down. And you'll see that we can get 2 units of flow there. There's 2 at the beginning and 2 at the end. And the key part, kind of the main part to focus on, is that section right there. Notice that we are using the residual capacity that we introduced on the original from the original graph. So basically, we're undoing part of what we did in that very first step along the blue, where we were saying we really didn't want to put 4 units down that way. We only wanted to put 2 units going through there. So just to update the graph so that we can see what's there, we subtract 2 off of each forward direction. And we will add 2 in each residual direction. Okay, and now we indeed, if you add all these up, that comes to 14, and that indeed is the maximum capacity. Again, it was one that hopefully you could identify yourself. Now, if we look at this graph at the end, you'll notice we can't push any more flow through. In fact, this top edge up here has 0 flow. This bottom edge coming out here also has 0 flow. This edge still has 1. Okay, so in theory, we could get out of there, and in fact, we could get from there. We could still flow up or we could still flow down, but then both of the others coming out of there, everything that's coming out of there is 0. So there's no way to get any flow to the sink. We're kind of stuck at this point. So this is the Floyd Fulkerson algorithm. It's something that you can use on a general graph and approach it that way. And it will find the max flow. You'll find the actual amounts that you have here, and you get an example of how that flow would work by looking at the capacity that got used up along each edge, if you want to. Okay, now there are some improvements on this. Floyd Fulkerson can be kind of slow, and it turns out there's a relatively easy approach that you can use to get better performance. And in fact, you should use this to get better performance. And that is something called Edmonds Karp. And the idea of Edmonds Karp, it's just a very simple variation on this, is that it is basically Floyd Fulkerson, where the initial path, or not the initial, but basically the paths chosen are the shortest in terms of number of links. Okay, so basically you can find this with a breadth first search. So if you just do a breadth first search on the graph, you will find the route that will give you the shortest path overall. And shortest in terms of the number of edges that you follow. Now, this does not mean that this is enough to make it a greedy algorithm. You still have to keep the residual capacities. You still end up doing sort of undoing stuff later. But by following this approach, you are guaranteed that you don't actually, basically it's going to cut down the asymptotic worst case of what's going to happen. And what can happen if you just use that. And so the idea here would be, for instance, that very first path that I took, where I went along the top edge up at the top, and then I kind of came down. This is the blue path. That's not the shortest path, right? It would have been shorter to just follow completely across the top edge. And actually, had I done that, this might have worked out better. But on a general graph, that's what you would do. You would take the shortest path along the way. Now, I'll mention that one way or another, you have to find a path through the graph. You have to find some path. You might as well use a BFS. There's really no reason not to use the Edmonds Karp approach to the problem. In the big majority of cases that I've seen, Edmonds Karp works fine for a max flow problem. It is still not asymptotically ideal, but it tends to work really well in practice. And generally, it's the one that I would just suggest you use if you are trying to implement max flow. It's kind of the default one that I think is easier to use. Now, there is a better one. I find it more difficult to understand and implement myself, but it does work more efficiently. There's some people who say, oh no, it's easy to code up. You can code it up. If you're interested in the code for this one, you can look in the book, but I'll just introduce the idea of it in here. And this is Denix Algorithm, and I don't know if I am pronouncing the name right, but Denix Algorithm is kind of like Edmonds Karp. In that you find the path, or I should say paths, with the fewest edges. And then you form something called a blocking flow along that path. You just among those paths. Okay, so after you've identified, say, the shortest paths, so up in this example, it might have been, I see 3 paths that are length 3, sort of just going over the top, through the middle, or down the bottom. All of those are length 3 paths. And so you would sort of handle them first. And the blocking flow is basically, you can think of it like the most you can put through the paths of length 3. So you push through as much as you can on paths of length 3. And then after that, there won't be any more paths of length 3. And so you now will look at paths of length 4, or whatever the next shortest amount is. And you keep working your way up until you've pushed all the flow through that you can. And you will repeat this. You will repeat this just like with Just like with Edmonds Karp, repeat it until you're done, until you can't push any more flow through here. Now, the process of forming the blocking flow is what's a little bit trickier, but it's basically like doing flow on that subset of paths as a way of thinking about it. So all of these algorithms are useful approaches you can go. There are some variations that are kind of not in this family. One of the most common ones that I won't go through at all is one called push relabel. So that's an alternative to max flow that you can look at if you're curious. If you have the book, you can look in the book and see a little bit more information about it. And then there are some algorithms that kind of specialize applications of these, and I'll mention one of those in a little bit because it turns out to be particularly easy for one of the max flow applications. Okay, so that is kind of our introduction to the algorithm. I hope that was clear. Again, if you want another example of a problem worked through, check the PowerPoint slides that we have or what's in the book, and you'll see another graph that you can kind of work through and see how the residual capacity works. Okay, so I'm going to switch just a little bit, and I'm going to talk a little bit about applications. And the first one is very simple. It is what's called the min cut. And you'll often see max flow and min cut kind of grouped together because they're basically the same thing. And so the idea of min cut is you want to ask yourself, what is the smallest set of edges in terms of cost that have to be cut to separate the source sink. Okay, so the min cut says how many edges, like what's the fewest number of edges total cost that I have to cut to separate the source and the sink. So I'm going to go back up so we can look at our problem that we had before, back to the original version of the graph. That's the one right over here. So that's the one that we'll look at here. And if you look at the graph and you say, what edges, if I want to cut edges to separate the source from the sink, what I'm basically doing is I'm creating a line through the graph in some pattern that's going to separate and cut those edges and cut the graph apart. And you can think of this as something like, say you're a saboteur and you're trying to disconnect the network or something, and you know how difficult it is to cut each link in the network, and so you want to find excuse me, you want to find what the cheapest way, what the easiest way to cut the network in two is, so that one person can't communicate to another one along the way. And so, for instance, this cut that I have would cost 5 plus 5 plus 4 plus 3. It would be 17. So that would be a cut of cost 17. And a different cut might be this one. That one would cut the graph in two. That would be a cut of cost 15. And if you look at this one over here, well, that's a cut of cost 14. Okay, so far that's the minimum that we found. And in fact, that turns out to be the actual minimum. So the nice thing about min cut is that the min cut algorithm is solved the exact same way as max flow. So you just solve this by running max flow. So even though the edges are no longer meant to be capacities, and instead they're sort of like a cost, the max flow algorithm still works here, and you get the min cut kind of as a byproduct. So you run max flow, and then you see which nodes are reachable from the source at the end. And so at the end, then, the edges to be cut are those in the original graph. You need to keep the original graph around. That go from a reachable node to a non-reachable. Okay, so let me illustrate what this means. We're going to first run max flow. So I'll go back to the graph that I showed you before. We'll run max flow on it, and then we're going to see which nodes can we reach in the final graph from the source. So at the end, when we're all done, which ones are reachable. And then the edges that we want to cut are ones that go from those reachable nodes to unreachable nodes. So if I go back here, and I'll use green. Obviously, the source is reachable from the source. And notice that I have this edge of length 1, or with capacity 1, so it's still possible to get to this node, okay, because there is some capacity there. I can't keep going to the sink, obviously, otherwise I could have kept running the max flow algorithm. But from that middle node, I've got capacity that goes down to the bottom, right? I could go along here, or I could go up there, up to that node. And basically all of those 3 nodes there are nodes that are reachable from the source, but I can't reach the sink. That's the only one that I can't reach. And so the cut that I have in my graph is going to be the edges in the original graph from those 3 nodes to the end. And that's basically a cut going like this. It's going to cut those edges. And if you remember what we had all the way up here, that would be these 3 edges, and those have a total weight of 14. The weight that they have is the same weight as the max flow. So the max flow weight is the same. The cost is the same. And if you need to know the actual edges, it's just those there that were along that path. So that's how we get our max flow process and use it to solve the min cut problem. Okay, let's talk for a minute about other types of applications that we have and some other ways that these flow graphs work. So there are cases where we will have, and most of these are pretty simple, where we'll have multiple sources. So you might have a situation where you have multiple sources and you even have multiple sinks. Okay, and you've got sources going in different directions, and there's some big messy graph here in the middle. And hopefully stuff is coming out to sinks there at the end. And the question is, how much flow is there through this system that flows this way? And by the way, they could even have stuff between sources or between sinks for all the good it does. Okay, so the way that this gets handled is we produce what you would call a super source and a super sink. And then you connect the super source and super sink to the sources, the super source to the sources and the sinks to the super sink, and then you run your standard max flow. So if you ever have multiple sources and multiple sinks, you just introduce 2 extra nodes, your sort of super source and your super sink, and connect up the graph that way, and now you have a standard max flow problem coming from here. So everything that, all of your remaining process works exactly the same as you would have otherwise. Okay, another thing that you'll often see, which we talked about back in regular graph algorithms, is if you ever have a vertex capacity. So if you have a capacity not just on the edges, but also on the vertices, remember that if I have a vertex that has a capacity of 5 and there's edges that are coming into it and some edges coming out of it, then I want to transform that into 2 vertices where there's a single edge of weight 5 between them, and then I have the edges coming into one and going out of the other. And so that way your capacity is still limited. You can only send 5 units through that node. So, so basically this whole thing is your original node. And that's just another way to look at it. So there are some kind of simple variations like that on the types of problems that you can run into and deal with them. Another problem that I'll mention while I'm talking about these kind of general approaches like that is what's called circulation. And circulation says I've got various points along the way, and lots of them are going to be sources. So they're producing stuff, and there's other things that are going to be sinks, and these can be kind of all spread out through my diagram. It's not really there. And the question is how much of the, think of the sources as excess supply and the sinks as excess demand. And there might be a particular level. So, I might have a lot of supply here, I might have a lot of demand over here, and a little supply and a little supply. And, maybe there's some demand here, and there's capacities on how everything's connected up. And the question is, how much of this can we meet? If we have capacities along all of these edges, how much of the supply-demand imbalances can be met? And you can easily picture how this is a useful approach that you might want if you were trying to kind of optimize distribution of stuff through a distribution network. Some product, and there's places you need more of it and places where you have excess, and how can you move it around to try to meet that excess, how much of it can be met. And so you can basically treat this kind of like we just mentioned, where you create a super source and you create a super sink, and those are going to provide the amount of flow, they'll provide the capacity then to the sources and to the sinks. So if this, was producing 5 and this had a surplus of 3 and this had a surplus of 1, then I would create edges that have 1 and 3 and 5 capacities to them. And basically that's providing them a source. And likewise, if this had a demand of 4 and of 2 and of 1 here, I would create my edges to the sink with capacities 4 and 2 and 1. Okay, and computing max flow through there is going to tell you how you can satisfy that entire thing. And there's a lot of problems that can be written as circulation problems. Okay, so there's one other category of problems that are particularly useful. So, before I get to that, let me mention one other kind of general thing before this kind of last category, which is going to be bipartite matching. Before I get to bipartite matching, one other one just to realize is sometimes you want to know how many edge disjoint paths are in a diagram. So if I have a bunch of nodes connected in a network, the question might be, how many different ways are there for me to get from the source to the destination without ever repeating an edge? And so you can actually solve this with max flow by basically putting a capacity of 1 along each edge. And the idea there is you either use the edge or you don't. So if it has a capacity of 1, basically if that capacity gets used, you're going to use that edge, and then you can't ever use it again after that. And so if this is my source and this is my sink, I could say, okay, I'll take a path there, and I might have a second path that goes like that, and I might be able to have a third path that goes like that. So in this case, I had 3 edge disjoint paths, and I can't have any more. And notice not every edge got used. There might have been other paths, but the most I can have is 3. And so that's another variation of the max flow problem. Okay, the last thing as far as a general type of problem that we have is what we will call maximum cardinality bipartite matching. And it's often abbreviated MCB. Okay, now what does this mean? So there's a lot of words there. What do they mean? Okay, so a bipartite graph, if you remember what a bipartite graph is, that is where you have a graph that you can divide into 2 groups that we can call left and right. And there are edges between nodes in the groups But there's no edges between nodes in the same group. So something like that is not allowed. You can't have an edge between two nodes in the same group. All of your edges are between the two different groups. And that means that you can categorize each of these. Like you can color these red and you can color these over here blue. And so you have a red and blue, distinction between the two sets of nodes, or, group one, group two, left and right, whatever you want to call it. So the idea, though, is that all of your edges, any edge you have, is only in that, is basically crossing that barrier between them. And bipartite matching says, how well can I match up one set to the next? Okay, so how well can I match up the red to the blue? Now, one thing is the only way you'd ever have a perfect match is if you had the exact same number of red and blue. Otherwise, there'd be no way to have a one-to-one matching. But assume that's not the case, assume you don't have the question might be, how many of these can I match up? How many is it possible to match up? And so you can solve this using max flow, but there's also another version of this. It still is actually max flow. It's just like you can implement it a little more easily. It's called augmenting paths, but the idea is still the same as max flow. And you can use that approach to actually figure out what things should be matched up ideally. Because the idea here, just to kind of illustrate, is imagine that I matched this red with this blue, okay? Well then, notice that I can't match anything with this one, and I might match that with that, and now I can't match anything with this, and now I'm done. I was only able to get two matches, but if you actually look at the diagram, it would have been possible to get three different matches, right? I could have matched that to that, and I could have matched that to that, and I could have matched that to that, so I could have actually had three. But if I chose badly at the beginning, I only got two. So if you want to do this as a max flow, then all of your edges, you just create your graph, all of your edges have flow one, you create a source on one side, you create a sink on the other, and you connect the source to the red group, and the sink you connect to the blue group, and that's it. Okay, so all of and that's it. You run max flow, and what that's going to do is it's going to identify some of the edges that are here in the middle that are, you'll perhaps flow through this top one here and match those two up, and then this capacity here will become 0, and you'll get your reverse capacity that'll be 1, and so on. And it's that reverse capacity of 1 that will let you undo a bad choice later on. So if you came through, in fact, I'll illustrate it very quickly. If I came through and the initial path that I picked was this path, okay, notice that I would reduce the capacity here to 0, but I would also introduce a reverse edge with capacity 1. And so later on, when I came through to the next node, which I'll use in yellow, when I came along this path here, I could come here and I could go like that, and I could still get there. And what that would do then is, as I adjusted that path, this would come back to be 1, and this would come back to be 0, and this one would have been 0, and so on. And the end result would be this link, and this link would have been the two that were left out of that, or that were the result of that. Okay, so it's that residual capacity. Again, the residual capacity is the thing that would let me go back along this route to kind of undo the choice that I made to begin with. So for maximum cardinality bipartite matching, so maximum cardinality means the most number of bipartite matches. Okay, cardinality is like the number. Bipartite graph, you're wanting to match one side to the next. And what's the biggest number of bipartite matches you can get? So that's MCBM. Okay, so I will mention that you don't actually have to run max flow to do this. You can get a slightly simpler version of it using something called augmenting paths or augmenting paths. So let me just mention augmenting paths real quick. Although as I describe this, you should say, wait a minute, that's exactly the same as max flow, and it really is. It is the same thing as max flow. So the idea of augmenting paths, and I'll try to use the same example I had before. And I had one here, and there. This one went here, there. Okay, so those were the edges that I had along the way. And so basically, each edge that we have in our diagram is either going to be marked as used or unused. And so you can think of it as, maybe I'll check it off with a purple once it's used, and if there's no check, then it's unused. Okay, and so the idea of augmenting paths is that we will start with an unmatched node, left node, and then we will repeatedly do two things. We will follow an unused edge to the right, and then I will check and see if that is an unmatched right node. If so, I will stop. Okay, so I'll follow an unused edge to the right, and then I will follow a used edge to the left. And then once I'm done, I will reverse the used, unused status of all the edges on the path. Okay, so let's just see what this looks like. So I'm going to start with a node here on the left. I'll start with this very first one, and I will pick an unused edge that goes to the right. Well, at this point, none of them have been used, so I'm going to pick this edge that goes there. So for that edge to the right-hand path, I will mark that used, and I get to this matched node, so I've matched to that node. So that node has been matched to one at the beginning. Okay, so I'm done, and that one, the purple path, has been used. Okay, so now I go to my next one. I'll use green for this. I go to this node, and I follow an unused path, and I say, did I get to an unmatched node? No, this one's actually matched already. Okay, this one has already been matched. And so what I'm going to do is I'm going to follow a used edge to the left. I'm sorry, I should have made it clear that we will repeatedly do this. We're going to sort of repeat this loop over and over. So now I'm going to follow the used edge back to the left, and then I am going to follow an unused edge to the right, and hey, I made it to a final unmatched node. That's this one. Okay, so now that I've reached an unmatched node, an unmatched right node, now I can reverse all of the stuff that was there. So instead of this edge being the one that was there, I mark it as unused, and I mark both this one and this one is used. And notice now I've matched those two up correctly. So that should look really familiar to you, that basically the used and unused is just sort of that residual capacity that got switched on or off. So it's following the same thing. I didn't have to explicitly show some source over here or explicitly show a sink over here. I'm just sort of assuming that that's the case all the way. But other than that, it's going to be the same process. And so when I come to the next node, I'll pick this one in yellow, I can pick an unused node that I had here. So I'll just show you a possible failure case is, in fact, let me, just so I can undo this later. Okay, so if I start there, I will go to that node. It's already been matched. So I can pick a used edge only. There's only one used edge, that's this one here. And I come back to that node and I'm to the left. And guess what? There is no unused edge coming out of that. So it is not possible for me to continue anymore. So that path did not work for me. I can try a different path, and sure enough, I get to that node right there, and that's now going to be my used edge. And then finally, when I get to the very last node, this one down here, I would try to follow something there. I would say, oh, I've reached a match node. I can follow a used edge there. And oh, I'm to the left. I do have an unused edge I can follow to there. I'm at a match node. I can follow the used one back to there. And now I'm stuck. I can't get any farther. So that did not work. And basically, I was not able to match that final node, which is obvious. There's 4 on one side, 3 on the other. There's no way I could have matched all of them. So augmenting paths is basically a simpler way of implementing max flow, but it's really the same idea. It's just you're keeping track of a Boolean of whether an edge has been used or not, rather than an integer that's keeping the capacity in each direction, or sort of 2 integers, the forward and the backward capacity in each direction. Okay, so that is the augmenting path approach. And again, that's an example of this maximum cardinality bipartite matching problem. And this is this type of problem where you want to match things in one group up with another, and you want to like make as many good matches as you can. This is a problem that actually comes up quite a bit. You can imagine, having people in 2 groups, and you have who's compatible with who, and you want to get as many, compatible pairs as possible. Well, guess what? That's an MCBM problem. Now, there are other variations on MCBM. There are sort of a min cost max flow thing. If you do MCBM on a bipartite graph, you can get things called like the maximum independent set or the minimum vertex cover. Those are problems that are normally NP hard, but if you know it's a bipartite graph, it actually becomes much simpler. So just realize there's all sorts of variations beyond the things that we talked about here. Now, there is one final topic that I want to talk about. And the final topic here is I want to give just a couple of quick examples. These are examples that I have pulled from the book. So if you want to read the book, you can do that. But these are examples that show how max flow can be applied to particular problems. And I'll describe those here for a minute. Okay, so let's take one example. This is an example of applications in computers. And the idea here is that we have a set of applications, and you can imagine these are, there might be 20 or more of these, and we have a set of computers that are capable of running the applications. Think of these as like high performance computers or something. And each program, so these programs or applications on this side and the computer over here, each program has certain computers that it can run on. Okay, so maybe this one can run on those, and this one can run on those, and so on. Okay, so there's some combination of which things can run on which computers, and perhaps there are a bunch more computers, but each computer can only run one program, and you might have, this is not going to be a great example here, but you might have some number of programs that you want to be able to run, and you might say, oh, I want to run 3 copies of this and 2 copies of that and 1 of this and 2 of this. And the question is, how many of those can I run on this set of computers that I have here? Well, the way we turn this into a flow problem, and this, again, just to be clear on this, we've got a set of programs. Each one we want to run, we have so many copies of it that we want to run. We have a set of computers, and then we have information about which computers can run which program. Okay, and it might not be obvious to you. It might, in this case, it probably is because we're talking about max flow, but in general, that might not sound like a max flow problem, but it really is. And so the way we turn it into a max flow problem is we will create a source and we'll create a sink, and we will connect the source up to all of the programs. And the capacity of these edges will be how many copies of the program we want to run. And the capacity of the edges on the other end going to the sink, those will come from each computer, will be 1. In other words, each computer, we would like to be able to run one program. And this is how many copies of each of the programs we would like to have. So we would like the source to be producing 3 of program 1 and 2 of program 2 and 1 of program 3 and 2 of program 4, for instance. Okay, so the edges here in the middle, since a program can only run on one computer, each of these is basically just going to be 1. Okay, and this might seem, and probably should seem, a whole lot like the MCBM problem, because you're kind of matching there. And in fact, if we made multiple copies of the program, so if we made 3 copies of the first and 2 of the second and 1 of the third and 2 of the fourth, it really would be identically the MCBM problem. In this case, because we have multiple copies of the same program, it's actually easier to do it as max flow, because we might be able to just, anyway, it's a simpler graph, and we don't have to repeat the nodes multiple times and reproduce a bunch of edges. Okay, but performing max flow through here, what that's going to do is it's going to give us some mapping of, programs to computers that hopefully will allow us to get as many of these through as possible. And yeah, in this case, we were able to get all but one of the programs through, and we were able to use up all of the computers with those lines that I drew there. So that just gives you an idea of how you can take a problem that maybe does not seem like a max flow problem at the beginning. It's a matter of which programs and which computers can get run, and phrase it as a max flow problem. Okay, another problem that comes from the book is one that is called Titanic sinking or something like that. And so the idea here is that we've got some like grid, and there's different things in the grid points. There's water, which we don't want. So, if there's water points, that's bad. You can have icebergs. So I'll put like a B or something for an iceberg. And an iceberg can hold people, it can hold lots of people, as many people as we want temporarily, but not permanently. So it'll just hold people temporarily. We'll have wood, and wood will have maybe a certain number of people that it can support and save. And so if they manage to get onto the wood, then they're safe. They're not going to freeze to death in the water. And then the other thing that is there is you could have ice, and ice might be something that can hold one person at a time. But as soon as the person leaves, the ice is going to sink, and no one else could get on it. So basically a person can hop on the ice, and then they can hop off onto the next adjacent thing, and then the ice is gone. Okay, and the question is how many people could be saved, especially if you have the starting position of people at some points along the way. And this is actually a max flow problem. The number of people you can save is basically the flow that you have through this system. Okay, and so the idea here is that you create a bunch of, basically you create a node for each cell. Okay, so we'll create basically a grid of nodes like that. If you have an ice flow, it will have a node capacity of 1. Okay, so there's just a node capacity of 1. If you have an iceberg, something that is like an iceberg that was the B, you can have basically as large of a node capacity as you want to along the way there. And then for the starting positions of people, you'll connect a source up to wherever the people started in the graph. Maybe they started on those 2 nodes and another one down here. So those are the places where your source is going to connect where the people start, and then the sink is going to connect to the wood. So if this was a piece of wood, and maybe the wood could hold 2 people, and this piece of wood could hold 1 person, and that piece of wood could hold 1 person. So there's a bunch of wood over here. Then that gets connected to the sink along with the capacity of each of those pieces of wood. And so the idea here is if I can push flow through, if I can start at the source and I can make my way through this system like that, that means that there is a person. So this person that I run into right here at the beginning, this one that I have along the green path, is going to start out by going to the person wherever they are at the beginning, and it traces their path through the process to get to a piece of wood at the end, which is right there. And then that is going to use up one of the two pieces of capacity that wood has. And then later on, if there's another person that I have that was similarly able to make some process there, they might use up another piece of the capacity or whatever. Okay. So the idea here in both of these problems and pretty much in all of the max flow problems is think about how you can phrase your problem as a way of pushing the information from the source to the sink. At every step along the way, you should be providing more information about what is happening. So in the Titanic sinking problem, as you move through this flow graph, that is showing the path that a person is taking between all of the different things. And so if they end up on a piece of ice, because it's got a node capacity of 1, there's only one person ever going to be able to use that ice. So if that person has the flow path through there, that means that's the person who used that piece of ice. Okay, so in this problem, your flow path shows you the physical path that a person takes. In this problem up here, the flow path shows you which program is going to get matched up with which computer, or how many of each program get matched up with each computer. So in any case, if you're trying to model a problem as a flow problem, think about what it means to go from the different types of nodes that you have and how a path from source to the sink, from the start to the end, how is that path that you're following modeling the thing that you want to happen? So either you're matching one thing to another one, or you're computing a person going through here, or there was an example that I used in the class recording, which is figuring out who's going to eat which pizza and how much of it is available. Sort of a flow through the graph there says this person is going to eat this number of pieces of this type of pizza. Okay, so that's what we have for max flow. It's an interesting topic. Once you start seeing problems that are max flow problems, you'll say, hey, that's cool. And you'll have a couple of nice ones, I think fun ones, that are on the homework for this week.